Okay, let's look at a couple of example problems. So this first example is a problem. It's a problem from the end of the chapter 1, 1.4-1. It's on function composition. So in part A, we're asked to sketch. They ask us to sketch the function ut minus 5 minus u of t minus 7. Okay. Now, I think this is all they asked for in the problem in the book. I like to define these as new functions. I find it helpful when I'm making substitutions for t. So there's a couple of different ways you could solve this particular problem. One is actually to sketch the individual components. So u of t minus 5 would look like this. This is a unit step that's shifted to the right by 5 seconds. So this would be the first component, u of t minus 5. Starts here at 5 seconds. And then is 1 for all t greater than 5. And then similarly, u of t minus 7 would be a unit step that starts at t equals 7 and goes on forever. So this is my t-axis. Again, both of these have a height of 1, u of t minus 7. And in this case, I'm going to subtract the 2. So the result would be, I'll show it right below. This is similar to some of the problems we worked in class last time. Here where they're both 0 up until t equal 5, where they're both 0. 0 minus 0 is 0 everywhere. In this interval from, this is 7. In this interval from 5 to 7, u of t minus 5 is equal to 1, u of t minus 7 is equal to 0. So that difference is 1. And then now for all t greater than 7, both functions are 1. And so 1 minus 1 is equal to 0, and will be 0 for all time after that. So again, this is that result. Okay. Just another way to do this is you can look at this in intervals, and I see this first component is 0 up until t is equal to 5, and then the second component is 0 up until t equal to 7. So I can break the problem down into respective intervals. So for example, both components are 0 for all t less than 5. And so I know that difference then is going to be 0. Now, at t equal 5, this component switches on. If we think of this as like a voltage that's switching from 0 to 1 volt, this one hasn't activated yet. It doesn't become active until t equal to 7. So I know in this interval between 5 and 7, this is the only component that I have to sketch. The other one is 0, and it's equal to 1. Okay. Now for all t greater than 7, this is 1, and this is 1. They're both active. So for all t greater than 7, I've got 1 minus 1, and that difference is 0. And so I get the same result. Okay. Let's take a look at part B here, where they ask us to sketch. It's a similar problem. Again, I'll call the result x of t. But now we're going to add these same two components actually. T minus 5 plus u of t minus 7. Again, just a quick sketch. These are the same two components as in the previous problem. And these are 1 for all t greater than 5 and 7 respectively. So this is u of t minus 5, u of t minus 7. I'm going to sketch their sum right below. Again, for all t less than 5, they're both 0, so the sum is 0. In the interval from 5 to 7, only this top function is non-zero, it's equal to 1. and so 1 plus 0 is 1. Now for all t greater than 7, they're both equal to 1, and 1 plus 1 is equal to 2. So these levels would be 1 and 2 respectively, and for all t greater than 7, the sum remains at 2. Again, you can break this down similar to what we did in the previous in part A. You know, for all t less than 5, both these are 0. For t greater than 5, this is 1. Until we get to t equal to 7, this is 0, so the sum is still 1. Then finally, for all t greater than 7, they're both equal to 1, and so the sum would be equal to 2, and you get the same result. Part C asks us to sketch t squared times u of t minus 1 minus u of t minus 2. Okay. We run into this difference of unit steps quite often, and so you'll want to start to recognize that as being a pulse, a rectangular shaped pulse. One way to approach this problem is to actually graph these two components separately. So graph t squared, and then also graph this pulse. So t squared would look like this. Okay. So I'll mark off 1 and 2. I know my pulse is actually between 1 and 2, and 3, 0, minus 1. And I want to sketch t squared. So t squared at t equal to 0 is 0, and then it's at t equal 1, it's 1. At t equal to 2, it's going to be equal to 4. So t squared is going to look like this. Sorry, my graphing is not too good. So this is what t squared looks like. And then the pulse just is non-zero between 1 and 2, where it has a height of 1. So this is this component, the u of t minus 1 minus the u of t minus 2 component. And now, in previous problems, I've been adding or subtracting these functions, but now I want to multiply them. But the procedure is similar. If I'm looking at this second component here, it's 0 everywhere except in this interval between 1 and 2. And then, so I know outside the interval between 1 and 2, where this function is 0, the product is going to be 0. So I know this product is equal to 0 everywhere outside the interval from 1 to 2. So I really have to only look at this interval between 1 and 2, where this component is 1, and this component is, the top component is equal to t squared. Okay, so I only have to graph the component t squared between 1 and 2. Okay. So at t equal to 1, this is going to be equal to 1. At t equal to 2, it's going to be equal to 4. Okay, so I just sketch in that little component. And again, this is 1 at t equal to 1, and then this is actually 4 at t equal to 2. And so this is the result. Again, you know, another approach, maybe a little simpler, is, again, if you recognize this is a pulse, this component is being a pulse everywhere outside the interval from 1 to 2, you know that I only have to sketch, I'm only going to have a non-zero product between 1 and 2, and then so I can just, at t equal to 1, the t squared component is 1, this pulse has a height of 1, so at t equal 1 I have this point. At t equal 2, t squared is 4. Again, this component is equal to 1. I could put in other points here, but I know it's going to have this parabolic shape. And so this is the resulting pulse. Okay. And the final part here in this problem, part D, asks us to sketch t minus 2 times u of t minus 2 minus u of t minus 4. And several different ways to attack this problem. We can do it similar to the way we worked in the previous problem. I see that the second component is actually a pulse of amplitude 1 between in the interval from 2 to 4. This first component is a line, okay, equal to t minus 2. So at 2 it's going to be 0, and it actually has unit slope. So at 3 it'll have a height of 1. At 4 it would have a height of 2. And so this line is going to look like this. So this is the t minus 2 component. And then the pulse is equal to 1 between 2 and 4 in this case. This unit step starts at t equal to 2, and then we subtract the unit step. That becomes active at t equal to 4. So in effect, what the product here is just pulling out this portion of this t minus 2 curve. And so the result, I'll sketch at the bottom here, between 2 and 4, where this is equal to 1, so 1 times this top function is 0 at t equal to 2, and it's 2 at t equal to 4. And it's just pulling out that segment of that straight line. So this would have a height of 2 at t equal to 4 and a height of 0. So this is what x of t would look like. Kind of maybe a slightly trickier way to do this would be to recognize, this looks like a delayed function, as does this. If I write y of t is equal to t and then times u of t minus u of t minus 2, and then sketch y of t. Okay. It's going to look like this. So now this is a pulse that's non-zero only between 0 and 2, and it's multiplying my t function, so it's going to look like this. This is what y of t would look like, a height of 2 here. Okay. And now I can see x of t is equal to y of t minus 2. And if I substitute t minus 2 in for t here everywhere, so this becomes u of t minus 2. This will become u of t minus 2 minus 2, which is t minus 4. So I can see that x of t, my original function that I want to graph, is equal to y of t minus 2, which is just y of t shifted to the right by 2 seconds. So if I slide this to the right by 2 seconds, I get this graph. It's another way to tackle this problem. You get the same result, of course, just a slightly different approach. I think the first approach is probably a little more straightforward. For the second approach, you have to recognize x of t as being a delayed function. Let's take a look at another problem. I won't work through all parts of this problem, but I want to work a couple problems that deal with the impulse, and in this case we're asked to simplify this function of omega. We've got j omega plus 2 over omega squared plus 9, and that's all multiplied by delta of omega. I think in most of the problems in the video lecture, and we worked with functions of time, but the properties here don't really depend on whether we're working in time or frequency or x or y, and the multiplication property still holds, and that's what we're going to apply here. According to the multiplication property, when you have a product like this of any function multiplied by an impulse, we just evaluate the function at the location of the impulse. This impulse is located at omega equals 0, And if we evaluate this function at omega equals 0, the numerator becomes j0 plus 2 or 2. The denominator is 0 squared plus 9 or 9. So the function we're multiplying by the impulse just reduces to 2/9, and then we keep the impulse. And this is a common mistake to say that the product is just equal to the function evaluated at the location of the impulse. According to the multiplication rule, the impulse stays. The function just reduces to a constant. It changes the weight of the impulse. So that's the multiplication property. Let's take a look at the other property of an impulse that we talked about. How an impulse behaves under an integral. So this is problem 1.4-4. We'll do part F, and we're asked to evaluate this particular integral. We're integrating from minus infinity to infinity of t cubed plus 4, and then it's delta 1 minus t dt. Okay. Now this one's a little tricky. If this were t minus 1 instead of 1 minus t, it's straightforward. The impulse is located at t equal to 1, and we could just plug in t equal to 1 and evaluate, and we're done. But it's safer in this case, or the safe approach, especially if t is scaled, multiplied by a number. It's safest to use a variable substitution. So I'm going to let lambda equal 1 minus t. Okay, so that d lambda would be equal to minus dt. And then solving for t here, t is then 1 minus lambda, and so dt is minus d lambda. And then so this reduces to I'm going to change the limits on my integration. When t is minus infinity, lambda will actually be plus infinity. And similarly, when t is equal to plus infinity, lambda will actually be minus infinity. Make a substitution in here for t cubed. That's 1 minus lambda cubed plus 4. And then now I've made this variable substitution. So the argument of my impulse is just lambda, and dt becomes minus d lambda. I'll pull the minus sign out in front, but then I can reverse my limits of integration. Doing that requires that I multiply through by 1, which will get rid of my minus sign. So this becomes 1 minus lambda cubed plus 4 delta lambda d lambda. The impulse here is located at lambda equal to 0, so I substitute lambda equal to 0 into this expression. I'll have 1 minus 0 cubed, which is 1, and then 1 plus 4, so the result is finally 5. That's exactly what I would have gotten up here, substituting t equal to 1, so I would have gotten the right expression. Again, in this case, it turned out not to matter with the variable substitution, but it's safest to get the expression in the form of the property. And the property, if you recall, had delta t minus t0. Sometimes the time reversal can actually make a difference. It's very important if you're dealing with a problem that's delta like 2t or something like that, that you make this substitution. Let's take a look finally at one last problem. This is problem 1.4-6, and we're asked to find I call this a running integral. This would actually be the output of an integrator circuit with input x of t. This is what we'd see then as the output of an integrator. The output is a continuous function of time as well. What's a little confusing about these problems is that one of the limits of the upper limit of integration in this case is a function of t. So we have to keep evaluating this integral as t changes. So in part A, we're asked to integrate, actually, we're given a graph of x of t. It's 1 out to t equal to 1, and it switches to minus 1, and then it's minus 1 out to t equal to 3, and then there's actually an impulse located at t equal to 3, and the impulse has a weight of 1. So 1, minus 1 here, 0, 1, and 3. Okay. We could formally integrate, and we could integrate. We have to break this down into regions. So I could, in the region between 0 and t, the function here is constant, and so I could formally integrate that. I'm going to kind of just actually do geometry and instead of going through the formal integration. I encourage you to go through the formal integration, but here as t goes from 0 to 1, I'm just going to be adding additional area to my integrand until until I get to t equal to 1. I'm going to be integrating over this entire first part of this pulse, which has area 1. So y of t is going to be 0 for t equal to 0. And then as t increases between 0 and 1, I start adding area. I'm integrating a constant, so I'll get a straight line or a ramp. And then at 1, I'll have the total area of this pulse. And that would be equal to 1. Okay. Now I start integrating this pulse. Okay. And so this has a negative amplitude, so I'm going to start subtracting, or decreasing area. When I get out to t equal to 3, this is going to have an area of minus 2. It's got a width of 2 and a height of minus 1, so the area would be minus 2, plus the area of this first pulse. So I'm going to get down to, at t equal to 3, I know I'm going to get down to minus 1. Okay. And again, I'll have a straight line connecting these. Now, if this were all the function, if this were all the components in the function, the result would stay at actually minus 1 forever. Okay. But at t equal to 3, I've got an impulse. When I integrate over the impulse, I get an area equal to the weight of the impulse. In this case, that area is plus 1. So at t equal to 3, I'm going to add in an area of 1. Well, I'm down at minus 1. I add in the plus 1, that'll take me to 0. And so this is the resulting function of integrating this over all time. And that's a little tricky. I did it geometrically instead of formally evaluating the integral. You might want to give that a try.